So I guess I'll say, like everyone else, it's really an honor to be speaking here. Okay, so the title of my talk is Convenient Coordinates, and by this I mean a coordinate system on a manifold. And even if you're the sort of analyst that only works on Rn with its one global coordinate chart, I think you do this all the time. This is exactly what you do when you scale. All right, so I want to start out with two kind of simple pictures. Let's say you come across this tiny little ant, and he's hard to see because he's at scale delta. But we all know exactly what to do. We consider the scaling map. Phi delta of x is delta times x, and we pull back by the scaling map, and then the ant becomes unit size, and he's easy to see, he's easy to understand. All right, now coming into our next slide, somebody's done something kind of terrible to our ant friend, right? But still, if you pick the right map phi, but in this case it's quite complicated. It's not linear like in the last one, but if you pick the right map phi, we can, again, turn him into a nice, beautiful unit-sized ant. So what I want you to take away from this slide is, over here, it's pretty rough. Okay? There's all sorts of rough stuff going on. But if you pick an appropriate phi, which in this case will also be rough, then you can turn it into something smooth, something that's easier to understand. All right? And so in some sense, this is a generalization of the last slide. Okay. Now this talk is going to have three parts, and the first part is the real part of the talk, and this is joint with Betsy Stovall. Okay, and I want to start the real part of the talk with two really simple proofs that we all kind of know. So let's take x a C1 vector field, and it's going to be non-zero at some point x naught. So here's the point x naught, and I'm going to draw the integral curve of x passing through x naught. Okay? Now consider the map phi of t is e to the tx applied to x naught. Now near the point x naught, that's a parameterization of this integral curve. And if I pull back the vector field x via phi, it just becomes this wonderfully nice vector field d by dt. And for today's talk, I want to think of d by dt as being smooth and normalized. That's like the best sort of vector field you could hope for. We understand d by dt. Okay, let's talk about a special case of what we just did up here. I'm going to take my manifold to be just the real line. I'm going to consider the vector field x is going to be delta times d by dx. My point x naught is just going to be the origin. And if you unravel all of this, this map phi of t is just going to be the usual Euclidean dilation map. Okay, and of course, if we pull back delta d by dx by this map phi of t, you just get d by dt, as we saw right here. All right, now these two proofs, in my head, they used to be really different. The top proof I used to think of as being very qualitative. Every vector field is d by dt, okay? And the bottom proof I used to think of as being very quantitative. If you really want estimates, then you're going to do the scaling, keep track of things. All right, but the top proof is a generalization of the bottom proof. And so if we keep track of constants in the top proof, you can think of it as a generalized kind of scaling. So today, we want to think quantitatively. All right, on to my second trivial proof. Let's take x1 through xn. They are going to be Cm plus 1 vector fields, and I'm just going to assume they're a basis for the tangent space at every point. Now I'm going to take the commutator of two of these vector fields, xi with xj. It can be written as a linear combination of the x's because they're a basis. But these coefficients, the best you can say about them in general is that they're Cm, because taking a commutator involves taking some derivatives. Okay, but the converse is not true. Just because the c's are Cm does not mean the x's are Cm plus 1. All right, let's see an example of this. If I took any C2 diffeomorphism of the plane, okay, so we're working on R2, and I pull back d by dx, and I pull back d by dy by this diffeomorphism that's just C2, they still commute, because pullbacks and commutators work how you want them to. Okay, so in this case, the c's are all 0, but the best you can say about these two vector fields is that they are C1. Okay. Now, the problem, the reason this wasn't an if and only if, and the reason we should have never hoped for it to be an if and only if, is this sort of statement here isn't invariant under diffeomorphisms. And that's exactly where the problem came up. All right, so it seems like what I've shown you is that you can't understand the regularity of the x's just by looking at the c's. I proved that to you, except it's a lie. And today we're going to see an appropriate if and only if. We're going to be able to understand the x's by looking at the c's. All right, here's going to be our setting. I'm going to take x1 through xn. They're going to be C1 vector fields on some C2 manifold M. And though it is unnecessary for what we're going to say, to make things easy, I'm going to assume they're a basis for the tangent space, and so they are linearly independent everywhere, and they span the tangent space everywhere. And our goal today is, or at least our qualitative goal, is to, if possible, find a coordinate system phi. So that's going to be a C2 diffeomorphisms from some Euclidean ball of radius eta onto some open set of the manifold. And what we're going to do is we're going to pull back these C1 vector fields by this diffeomorphism. We're going to call those y's. Now, if you were a physicist, you might say this is writing the vector fields x in the coordinate system given by phi. And what we want is to understand when can we pick this coordinate system so that these y's are smooth. When is there a coordinate system in which the x's are smooth? Or maybe we only want some finite level of smoothness, CS. Okay, that's our qualitative goal, but remember we want to be quantitative. Our quantitative goal is the following. When can we write these y's, so I'll write them as a column vector, as a perturbation of the gradient? So I'll think of that as I plus A times the gradient, where A is a small matrix, so let's say its matrix norm is always less than a half, so that this is invertible. And A of 0 will be 0, and A has whatever desired level of smoothness we want. When can we write these y's as a perturbation of the gradient? Okay, so those are our goals for today. And now remember, we have to work diffeomorphically invariantly. We saw that earlier on. And so I'm going to introduce for you some function spaces on this C2 manifold M. Now remember, it's just a C2 manifold, and so I can't talk about smooth functions. That's not allowed. But I'm given these vector fields x1 through xn on M. And what I mean for a function f to be Cm with respect to these vector fields x is the obvious thing. I take all mth order derivatives of f, and I insist that they be continuous. Now, these vector fields don't necessarily commute, so I have to do all different possible orders. This is some sort of ordered multi-index notation, but whatever, it's exactly what you would write down to write down the Cm norm. Now, a quick comment about the Cm norm. If I take a diffeomorphism psi, and I pull back f via psi, and I pull back the vector fields via psi, and I pull back the manifold via psi, the norm doesn't change at all. Pullback is an isometric isomorphism of these Banach spaces. And what this means in practice is you can compute this norm in any coordinate system you want, and you'll get the same number. Okay? Exactly the same number, no matter what coordinate system you're using. All right, so those are the spaces Cm. You might believe that I can also define the appropriate Holder spaces. I won't write it down, but it's not hard. And maybe you'll even believe I can define the appropriate Zygmund spaces. Now, if you don't know what Zygmund spaces are, it's okay. Just think of Zygmund spaces as Holder spaces. So ZS, think of it as CS. That's almost always right. Not quite always, but almost always right. Okay, and being C infinity with respect to these vector fields x just means being Cm for every m, obvious thing. And you can also define what it means to be real analytic, which is an estimate of the growth of these derivatives. Okay. So these are our diffeomorphically invariant function spaces. Okay, so back to our setting. Let's remember, we have x1 through xn. They're going to be C1 vector fields. They're going to be a basis for the tangent space. We want to find some coordinate system which we're calling phi. It's a coordinate system near some point x naught, and we're going to call the y's, they're going to be the x's written in that coordinate system phi. So yj is the pullback of xj via phi. Okay? Now, again, the commutator of two x's can be written as a linear combination of the x's, but the best you can say about these c's is that they're continuous. The x's are c1, so the c's are just continuous. Okay, and here is the qualitative theorem for the qualitative theorem for the real part of the talk. There exists a coordinate system phi such that these y's are c infinity if and only if the c's are c infinity with respect to x near x naught. Okay, let's unravel this a little bit. The right-hand side is diffeomorphically invariant. You can check that in any old coordinate system you want. That tells you exactly when there's a coordinate system in which the y's are c infinity. One way of this if and only if is obvious. If the y's are c infinity, that means the x's are c infinity in some coordinate system. In that coordinate system, the c's are c infinity, and this is just the diffeomorphically invariant version of that. So it's the converse that's the trick. All right? You can do this for a finite level of smoothness. If you wanted the y's to be Zygmund of order s plus 1, you can do that exactly when the c's are Zygmund of order s with respect to the x's. And similarly, real analytically, if you want the y's to be real analytic, the c's just have to be real analytic with respect to the x's. So any level of smoothness you want, you can get just by checking on the c's in any coordinate system. All right. I remember I said that them being a basis for the tangent space wasn't really necessary. All you really need is this formula right here, and once you have that, this theorem goes through. Okay, but our goal was the quantitative kind of result, so let's go quantitative now, the quantitative theorem. And again, we're given these x's x1 through xn, and the commutator of xj with xk is a linear combination of the x's. And what we want, it's going to be a quantitative theorem, so there are going to be estimates. And we want the estimates to be diffeomorphically invariant. We want the estimates to only depend on things like the zsx norms of the c's. Okay, and here's the theorem, joint with Betsy Stovall. You can pick this coordinate system, there exists a coordinate system phi on a neighborhood of the point x naught and m. Now this eta, so we're working on the Euclidean ball of radius eta. What is eta? I want you to think of eta as being 1. What I really mean by that is you can estimate it in terms of completely diffeomorphically invariant quantities. There are some topological constraints that I don't want to actually write down right now, but think of eta as being equal to 1. Now the y's are going to be the pullback of the x's via phi, and then the theorem says the y's in this coordinate system are perturbation of the gradient. They're I plus a times the gradient, where a is a small matrix, and a is Zygmund of order s plus 1. So the c's are Zygmund of order s, the a is Zygmund of order s plus 1. Yes?
Yeah, I'm sorry to interrupt you, I apologize. But when you said you don't need it to be a base, does that mean that you allow the rank of the x1, xn to jump?
Yeah, so what the theorem would then be, you would just have like an injectively immersed submanifold, and you would just work on the manifold. So this is a Frobenius type thing. You Frobenius first, and then they span. Yep, that's right. Okay. All right, so this A is Zygmund of order s plus 1. And the actual theorem has a whole bunch of really useful estimates that I won't write down. And this is based on work of Nagel, Stein, and Wainger, Tao and Wright, and previous work of mine, and I'll talk about all of that history in a little bit. But before I talk about that history, what I want to do is I want to show you how quantitative theorems like this can be used as scaling maps, because that's how I talked about it all at the beginning. So, and that takes us back to the sort of scaling that Nagel, Stein, and Wainger did in their original paper on the subject. So I want to tell you about what they did. So here's the setting. x1 through xr, they're going to be C infinity vector fields now, so everything is smooth, and they're going to satisfy what's known as Hormonder's condition. And let me remind you what Hormonder's condition says. It says you start with these vector fields x1 through xr, You take their commutators, xi with xj. You take the commutators of order 3. You keep on going up to commutators of some big finite order m. And then Hormonder's condition says that this list of vector fields spans the tangent space at every point for some finite number m. Now, what we're going to use is something a little weaker than this. We don't really care that they span the tangent space at every point. We care about something else. Let's say we take v, which is going to be a commutator of order e bigger than m. Let's say we keep on going on in this list. Well, then v can be written as a C-infinity linear combination of the commutators of order less than or equal to m, because everything can, but v in particular can. Okay, so v is this linear combination of VL, where VL is order DL less than or equal to m, so up in that list. All right, so what I want to do now is I want to take a little tiny red delta and put it in front of those x's. So there it is. And so now I want to see how this red delta propagates through Hormonder's condition. Now in the second line, when I put a delta in front of xi with xj, a delta squared comes out. In the third line, a delta cubed comes out. All the way down into the mth line, a delta to the m comes out. Okay. Now this v was a commutator of order e bigger than m, so it gets a delta to the e. But I'm going to be a little bit clever here, and I'm going to write delta to the e as delta to the e minus dl times delta to the dl. Now, delta to the dl vl was something up in this list up here. Okay? E is bigger than dl because e is bigger than m. dl is less than or equal to m. So delta to the e minus dl is a small number. Delta is small. So delta to the e minus dl times cl is some C-infinity function uniformly in delta. Okay, what does that tell us? Well, that tells us if we look at this list of vector fields up here with the delta, and if I take the commutator of any two of these vector fields in this list, it is going to be spanned with coefficients which are bounded uniformly in delta by vector fields in this list. Okay? That was exactly the main hypothesis of the quantitative theorem. So the quantitative theorem applies uniformly in delta. The commutator of any two of these is spanned by these uniformly in delta. All right, so what does the quantitative theorem give us? Well, it gave us this map phi delta. And I'm just going to pull back everything by phi delta. Now in the first line, I'll call the pullbacks of the delta x's, I'll call them y1 delta through yr delta. Pullbacks and commutators work exactly how you want them to. And so the pullback of the second line is just the commutator of these two things. And that goes, pullback of the third line is just the commutator of these, all the way down to the commutators of order m. Now, what the quantitative theorem says is that if I look at this finite list of vector fields, it says they span the tangent space and they are C-infinity uniformly in delta. So you should think of them as being unit-sized. They span the tangent space uniformly in delta, but they're also bounded uniformly in delta. Okay? Another way of saying that is just that y1 delta through yr delta satisfy Hormonder's condition uniformly in delta. Okay? To put that all in a simple way, we took the case of delta is small, we had multiplied by the small number delta, and we turned it into the case of delta equals 1. So think of that as scaling. Delta small turns into delta equals 1. All right, so since Nagel, Stein, and Wainger did this, it has had a ton of applications. If you look up on Google Scholar, it gets cited like 1,000 times. So it's been used a lot. I'm not actually going to tell you too much about those applications, but it's this generalized sort of nonlinear scaling, and it can be quite useful. All right, I want to show you, so this is the algebra of what Nagel, Stein, and Wainger did. I want to show you the geometry.
So when you say it satisfies the harmonic condition uniformly, do you mean like the Gramian has a lower bound?
Yeah, there's some determinant with a lower bound, right? They span the tangent space uniformly, that's right. Okay, so if you take these vector fields delta x1 through delta xr, there's a natural unit ball associated with them. It's called the sub-Riemannian ball of radius delta. And the way it's defined is as follows. You start at the point x, that's going to be the center of our ball, and you're allowed to travel for 1 unit of time, but your speed is going to be spanned by these delta x's. So if delta is small, you're going very slowly, and so this is a very small ball. Okay? Delta is small, you can't get very far, and we're thinking of delta as small, so let's make the ball small. All right. Now, Nagel, Stein, and Wainger, they gave us this map phi delta. And what does phi delta do? Well, let's say you're working on this tiny ball here. You're trying to do some proof. Everything is small. You end up dividing by small numbers. Everything is terrible. But Nagel, Stein, and Wainger gave us this map phi delta. And it takes this tiny sub-Riemannian ball and turns it into the Euclidean ball of radius 1. And on this Euclidean ball of radius 1, you have access to really all of calculus. And often it turns into some like proof that you might see in a paper of Hormander or Kohn, something with pseudo-differential operators all over the place. Okay? So you have this proof over here that you want to do, this result over here you want to do. You turn it into a result on the Euclidean ball of radius 1. You do all the normal harmonic analysis, and then you push it back, and you get results at every scale uniformly in the scale. So you're able to do results at the small scale by working at the unit scale. All right, I drew this picture here centered at some point x, but if you have some manifold, you have the same picture at every point x, and this map phi delta actually depends on the point x. All right. So as x varies, you have all these coordinate charts phi delta. In other words, you have an atlas. Okay? And so for a fixed delta, for each fixed delta, you get an atlas on the manifold. And what does this atlas do? Well, at the scale delta, it sees that scale as being equal to the unit scale. Now, if you're working intrinsically on a manifold, you're always allowed to change which atlas you're doing. And so one way of interpreting what Nagel, Stein, and Wainger taught us is that in sub-Riemannian geometry, there's no such thing as a small scale. Every scale is the unit scale. Just you have to pick the right atlas. And they gave you the atlas. All right. So some history about all this stuff. Nagel, Stein, and Wainger, I told you what they did. You start with vector fields x1 through xr satisfying Hormander's condition. You multiply them all by a small number delta. And then they gave you this diffeomorphism that gets rid of the delta. And about the same time, Charlie Pfefferman and his student Sanchez Calle did a similar thing. Later on, Tau and Wright wanted to do the same thing, but they wanted to multiply each of these x's by different numbered delta. So you start with Hormander's condition, you want to multiply by different small number delta, and you want the same thing, you want to get rid of the deltas. And you can't do it always. They showed exactly when you can do it, and that's when these deltas are weakly comparable. So delta j, some large power, is bounded by delta k. And when you have this, then the same proof goes through, and you can get rid of the deltas. I got interested in this. I wanted to understand when you don't need to have weak comparability, and so I gave the necessary and sufficient conditions about when you can do this for all deltas. I won't write them down, but a highlight of it is when these are real analytic, you can do this for all deltas uniformly in the delta. You don't need weak comparability. All right, and then there's this theorem that I told you today, and what it has over these previous ones is everything is completely invariant under arbitrary C2 diffeomorphisms. So up here, we always assumed these vector fields were smooth, and then we multiplied by a small number delta. So you're always working with smooth, small things. But smooth and small, they're not concepts that are invariant under C2 diffeomorphisms. So now we can work sometimes with rough and large things, and we have exactly when you can do that. All right, so now the second part of the talk is the complex part of the talk. And back when I was Eli's student, I got into my head that I wanted to apply these same ideas in the complex setting. And immediately when I started doing it, I ran into a problem, and I want to tell you about that problem. Okay, so here's our setting. We're going to take L1 through Ln. They're going to be a basis for the anti-holomorphic vector fields, and I'll make them smooth and small. So here's what I want you to think. We're on Cn, and Lj is going to be a small number delta j times some C infinity linear combination of d by dzk bars. Okay, but the b's are just C infinity, or maybe even just finite level of smoothness. And what you want is you want a rescaling. And so you want to come up with some diffeomorphism phi such that when you write the L's in this coordinate system, they are a perturbation of the d by dw bars. That bar didn't quite make it through, but there's supposed to be a bar on top of that w. Yes. Well, you could conjugate everything. If there's no bar, it's okay. But got to pick one. Okay. So this is supposed to be a perturbation of d by dw bars, and a of 0 is 0. So when can you do this? When can you get rid of the deltas? That's the question. All right, and so there's an obvious guess of what to do. We know the necessary and sufficient conditions now on when you can rescale real vector fields. Now we want to rescale complex vector fields, so why not just rescale their real and imaginary parts? Okay? So why not just apply Nagel, Stein, and Wainger's theorem or one of these later theorems and rescale their real and imaginary parts? Well, let's look back at what we want to do. We want to pull back a basis of the anti-holomorphic vector fields, and we want them to be anti-holomorphic, if you have that bar there. And that's really the definition of phi being holomorphic. So what we want now is we want a holomorphic way to rescale these things. And so you go back to Nagel, Stein, and Wainger's proof or any of these other proofs, and you're like, well, if I plug in these real and imaginary vector fields, do I end up with a holomorphic phi? And you just don't. I mean, this fails. And it fails because that's the way mathematics usually works. If you start with a CM thing, CM things pop out. If you start with a C infinity thing, C infinity things pop out. But here I want C infinity, or maybe even finite level of smoothness, and then have a holomorphic thing pops out. And at the time, I couldn't even imagine how that would happen. I don't know when that happens. So I gave up for a while. But I came back to it recently, and it turns out a different coordinate chart phi does work, so you can do this. So let me state the theorem for you. Here's the qualitative theorem. I won't go through the quantitative theorem, but here's the qualitative theorem. L1 through Ln, they're going to be C1 complex vector fields now on a C2 manifold M. And let's make L1 through Ln and their complex conjugates a basis for the complexified tangent space. So in your head, think of L1 through Ln as being a basis for the anti-holomorphic vector fields. So these will then be a basis for the holomorphic vector fields. But now we're on some abstract manifold, so we can't really talk about those. And we're going to assume two things. Well, this is the big assumption. We're going to assume the commutator of Li with Lj is written as a linear combination of the L's. Okay? And that's really an assumption because the L's aren't a basis, so we're assuming that the commutator. This is certainly true if they're all anti-holomorphic. And then this is not an assumption because the L's and the L bars are a basis. We'll write Li with Lj bar as a linear combination of the L's and the L bars. And let me just take the x's to be the real and the imaginary parts of the L's. So the x's now are real vector fields which span the tangent space at every point. And here's the theorem. For any s bigger than 1, locally you can pick a coordinate chart phi, coordinate system phi, such that if we write these L's in the coordinate system given by phi, they are anti-holomorphic. They're spanned by the d by dw bars, and they're Zygmunt of order s plus 1. If and only if the C's, the D's, and the E's are Zygmunt of order S with respect to x. So that's our diffeomorphically invariant condition about when we can do this. Again, one way is obvious. The left implies the right is obvious. The right implies the left is the trick. Now, there are two aspects to the left-hand side. Let's say I forgot about the regularity that I wanted here. All I wanted was to get the phi stars of the L's to be anti-holomorphic. This is called the Newlander-Nuremberg theorem. It's classical. Let's say I got rid of them being anti-holomorphic and all I wanted was the regularity. That's a special case of the real theorem from before. So the idea is to get both the Newlander-Nuremberg theorem and the real theorem simultaneously in a complex theorem. And there you go. All right, and there is a corresponding quantitative theorem, which I won't bother to state today, but it's the scaling we wanted in the holomorphic category. You can scale via holomorphic maps now. All right. I talked about this earlier. So Nagel, Stein, and Wainger, they taught us how to scale real vector fields. And the way they sort of introduced it, and the way we talked about it before, it gives you a quantitative theory of what's known as sub-Riemannian geometry. Those balls that I had before, they gave us a quantitative theory of that kind of geometry. Now, I've told you how to scale complex vector fields with holomorphic maps, and I want to call this a quantitative theory of sub-Hermitian geometry. All right, well, what is that, other than just something I made up? Sub-Hermitian geometry is, you want to make a sub-Riemannian geometry, but sub-Riemannian geometry, it's based on these real smooth vector fields. But let's say you're on a complex manifold, and you want to base sub-Riemannian geometry on, say, smooth anti-holomorphic vector fields. Well, now you can do it. But the thing that's so important is now you can do it and you can develop all of or a lot of the theory of sub-Riemannian geometry just using holomorphic maps. Now, if you weren't using holomorphic maps, you wouldn't be on a complex manifold, so you wouldn't be doing anything special. But you can do it all intrinsically on the complex manifold with holomorphic maps. And so hopefully this will be applicable in several complex variables. All right. So I wanted to say a little something about the proofs of all these things, but instead of trying to give an overview of the proof, what I want to do is I want to talk about a classical proof that really influenced a lot of this, and I think is a wonderful proof, and so I hope people will enjoy seeing it. So this is Malgrange's proof of the Newlander-Nuremberg theorem. I think it's a really beautiful proof, and I hope that everybody gets a little something out of me going through it for you. And I should say, I'm not the only person that loves Malgrange's proof of the Newlander-Nuremberg theorem. Nuremberg himself called it ingenious and daring. So you guys can judge whether or not it's daring. All right. So here is the setting. I'm going to work on C2. And C2, we'll start with this complex vector field L1, which is going to be d by dz1 bar plus a linear combination of the d by dz's. So this is going to be, say, some C infinity linear combination of the d by dz's. And I'll write that in matrix notation. It's d by dz1 bar plus the row vector a1 times the column vector d by dz. And there's going to be another one, L2, d by dz2 plus a2 d by dz, and we're just working on C2. And we're going to assume that A1 and A2 at 0 is 0, so at the origin, L1 is just d by dz1 bar, and L2 is just d by dz2 bar, and we're going to assume that L1 and L2 commute. And the Newlander-Nuremberg theorem in this setting says near the origin, you can pick a coordinate system phi such that if I pull back these L's via phi, they are anti-holomorphic. That's what the Newlander-Nuremberg theorem says. I want to say a few comments about what the Newlander-Nuremberg theorem actually is. We saw it a little bit earlier. It's some abstract thing on some manifold, but it's pretty easy to reduce it to this theorem here. And of course, this theorem is really about n, not 2. You should have n vector fields on Cn, but same proof for n and 2, so let's stay with 2. Okay. Francois told us in his talk that when A1 and A2 are real analytic, everybody knows how to do it. It's pretty easy to do. So today we are going to just reduce it to the real analytic case. Okay, and also A of 0 is 0. We're working near 0. I want you to think of A as being very small. So these are just a perturbation of d by dz bar. Okay, so I've rewritten the setting. Here's L1, d by dz1 bar plus A1 d by dz. Same thing for L2, and they commute. So let's just do the computation. What does it mean for them to commute? Well, I've written it out. So there's the term where d by dz1 bar lands on A2, term where d by dz2 bar lands on A1, and then these terms where A1 d by dz lands on A2, and I wrote them on the other side. Okay, now the left-hand side is linear in A, the right-hand side is quadratic in A. and A was small. And so you're supposed to be thinking of the right-hand side as being much smaller than the left-hand side. And so to make everything simple, let's pretend it's 0 for a moment. Okay. And this now, I think, lets us really get to the heart of what's kind of hard about dealing with these vector field questions. This linear partial differential operator here is certainly not elliptic. It's not hypoelliptic. And this goes back to the thing from the very beginning of the talk. You can have two vector fields which commute, and they don't have to be C infinity. Okay? And that's really closely related to the fact that differential operators like this are not elliptic. All right, so the first clever thing Malgrange tells us is, all right, this is not elliptic, but let's imagine we knew a little bit more. Let's imagine we also knew that dA1 d by dz plus dA2 d by dz2 was 0. Let's suppose we don't know this, but let's suppose we did. All right? Well, this system of equations is elliptic. So now this is something good, something we can deal with. All right, let's go back to our original equation here. There it is. And when you put all this together, remember A was supposed to be small. When you put all of this together, if you look at this system of equations, this is a real analytic nonlinear system, which is elliptic at the point A equals 0. So that's exactly what we said. And it is a classical result that solutions to real analytic elliptic systems are real analytic. And so you conclude that A is real analytic. It's not an easy. Okay. All right. Yes. Okay. And so now we know A is real analytic in this case. And so we're done, because I told you that this proof is now easy once you know that A is real analytic. Feels like we haven't done anything, because I've just given you a special case of something I told you was easy. But what we have done, what is great here, is it's easy to check if A satisfies this equation. It's hard to check if something is real analytic. It's easy to check if it satisfies some differential equation. You can just sort of compute it. So that's what we've gained. And so our goal now is to reduce to this easy to check situation. All right. So now we're going to try and reduce to that setting. Again, I've written up our setting up here. We have L1 and L2, and they commute. And what we want now, what will finish this off, is if we can find a diffeomorphism H. Well, all we care about are the spans of these L's. So we're going to push forward L1 and L2 via H, and I'm just going to care about their span. And we want to be able to pick H such that the V's have the same form as the L's. This is some new coordinate system, but the same form as the L's, plus our excellent extra equation here that makes everything real analytic. All right, so if we can pick this H, then we'll be done. The V's will be real analytic, and then we know how to do the proof. All right, so we want to pick this H, but what we want is, in the end, just some differential equation to be satisfied. So what you can do is just plug in an abstract H, take derivatives, and see what needs to happen. Straightforward. And you find out that this will happen when H and A satisfy some nonlinear partial differential equation. It's going to be first order in A and second order in H. But whatever, some nonlinear partial differential equation. When it's satisfied, the H that satisfies it will do exactly what we want it to do. Now, I won't write down what f is, but I'll just tell you it is an explicit smooth function that you can write down. And this differential equation here is going to be elliptic at A in H at the point A equals 0. H is the identity. Okay, so if you set A equals 0, take the derivative in H. It's a second order elliptic differential operator when H is the identity. All right. And that is exactly the condition you need to apply the Banach space inverse function theorem to solve for H as a function of A, as long as A is small. H will be near the identity. A is small. You can write H as a function of A and have it satisfy this equation. And then you're done. That's the H you needed. So just some abstract inverse function theorem finds the diffeomorphism you need, and everything's real analytic. All right. I think that I want to talk a little bit about what happened here. So what we wanted here was to apply the implicit function theorem. And the way that works is you set a equals 0, you take the derivative in h, you want the derivative in h to be a right invertible map. That's how you would solve like this. All right, like I said, the derivative in h, because this is second order in h, the derivative of h at h equals the identity is going to be a constant coefficient, elliptic, partial differential operator of order 2, linear. And we want that to be invertible. And it's invertible, we all know this, it's invertible on Siegmund spaces. It's not invertible on Holder spaces, Lipschitz spaces, CM spaces. It's invertible on Siegmund spaces. They work exactly how you want them to on Siegmund spaces. And that's really why I had to use Siegmund spaces today. I wish I didn't, but had to use Siegmund spaces today because of this. Okay, and so Malgrange, of course, he taught us how to prove the Nylander-Nuremberg theorem, as I showed you. But I think he gave us something more than that, which is the following. You have all of these problems involving vector fields. And you can try applying these classical ideas of Nagel, Stein, Wainger, Tau, and Wright, and they get you a lot of the way. But every once in a while you run into a problem where they're not quite good enough. They don't quite give you the full results you need. And this gives us an extra tool. Because you get to the point where you're stuck, and then you try and be like Malgrange and turn it into a nonlinear elliptic question. And so you go through his little thing, and it's really been very useful. So whenever you're stuck on one of these vector field questions, maybe you can turn it into an elliptic theory question, which I think is amazing because, as we saw, these things are not elliptic at all. But somehow Malgrange let us turn them into an elliptic thing. All right, I'll stop there. Thank you.